Hey everybody, in this video we're going to practice graphing the derivative graph, that is f prime, from the graph of f of x. If you want to follow along, the links to the companion worksheet are in the description below, so let's get started. So what we have here is we've got a function graph, and what we want to do is we want to say what is the derivative at any point, that is the slope. Now we start with a line, and a line is pretty simple because the slope never changes. And so from here to here to here, it's always the same. In this case, the slope of the line is always 1. So over here, I can sketch out my graph of the derivative. And really, all I need to do is label this one spot on the y-axis. And so there's my graph of f prime of x. There's y, and there's x. There's really no other distinguishing point that I need to make note of. And so we have just a simple horizontal line there. So looking at number 2 now we have a curve. So now things get a little more interesting. So what I always tell people is first try and find any spots where the slope is 0, where the tangent line would be horizontal. And there is one right here. So that's a good point for us to anchor from, because that tells us that our slope is 0, so the f prime graph is also going to be 0 at that point. Now off to this side, the slope is positive. So here, if I were to estimate, this has about a slope of 2 at x equals 1. And so at x equals -1, because this is symmetric, this should have a slope of -2. And so what we have here is an f prime graph that looks linear. And if we think about a quadratic, what its equation would be for its derivative, it would be a line. So that's what f prime is going to look like for number 2. For number 3, there is no point where the slope is 0. It's always positive. Here it's very slight, but then as it goes along, it goes up and up and up. So if we look here and we try to estimate this slope would be about 1/2 or so. So if I graph, there's my point at 1/2. Now off to the right, the slope is going to keep growing, but here the slope is going to be not as much. But exponential functions never cross this x-axis. And so actually for an exponential function, its derivative graph looks very much like itself. And if you think about exponential functions like e to the x, the derivative of e to the x is e to the x. So the derivative graph of an exponential function is itself an exponential function. Moving on to number 4. Here again, we don't have any points where the tangent line is horizontal, so no slopes where f prime is 0. So let's look over here. Here it's always negative. It starts slightly negative and then becomes more negative. Here it's very negative and then becomes slightly negative. So I can draw my axes, and looking mostly down below, here's x and here's y. So if I look at 1 and I had to estimate, that slope is roughly -1. So we'll put that point down there. And this is the reciprocal function, so this is symmetrical about the origin. So these 2 points both have the same slope of -1. Now as x gets bigger, it becomes less negative. So that means it's going to approach the x-axis. Whereas if you start at 1 and go closer to 0, it becomes more negative. And it just continually gets more and more and more infinitely negative. Over here, if we go from -1 and head towards 0, it also gets infinitely more steep. And then as we head off to values less than -1, the slope increases, but never crosses 0. So here's what your f prime graph will look like for a graph that looks like this. For the 5th one, we do have 2 points where the slope is 0, right here and right here. So that's a good starting point for us to work with. Now between them, the slope is positive. Greater than this point, the slope is negative, and less than this point, the slope is negative. So we are going to need both positive and negative values here. Now both of these points don't fall on integers. They fall between -1, -2, and +1 and +2. And so here it starts positive, gets more positive, and right about here is where it's the most positive. And this line seems to have a slope of about 2 at that point. So between here, and then it has to come back down. There we go. And then after that, it's going to come down. And if you notice, the graph starts to level off, as in starts to become like a line. And it does that here, and it does that here, and it does that here. If you notice the shape of this graph, this is a sine graph. And so we know that the derivative of this is a cosine graph. And so when a curve becomes linear, what happens is it starts to level off. So this graph is also going to level off, just like that. So there is our graph of f prime. Moving on to number 6. This one doesn't have any negative values. The slope is always positive. And so here it's very positive, and then it levels off until it's almost linear, and then it starts to pick back up again. And it doesn't seem to go past 4 or -4. Whereas at 0, the slope is positive, but not by much. And as you approach 4, the slope becomes more and more positive. And as you approach -4 from the left, the slope also becomes very positive. But it will never cross -4, and it will never cross 4. So this is our graph of f prime of x. So looking at number 7, this is interesting because we have an absolute value graph, and with absolute value it's made up of 2 lines, but the slope is never 0. Here the slope is negative, and then it instantly changes to a positive. So we will need both negative and positive parts to this graph. And so here it looks like our slope is about 1, and here our slope is about -1. So if I label these, so this part goes off that way forever. Here this goes off forever this way. Now the interesting point is that the slope at this spot doesn't exist, because we cannot zoom in and make it look like a line. It's always going to look like absolute value there. And so if we tried to take the slope from the left and the slope from the right, they won't match up. So that means for our f prime graph, that spot has to be an open circle, because there is no slope at that point. Number 8, this is an interesting one. Here we have the stair-step function. And for each piece of it, the slope is 0. It's a horizontal line. It's not rising and it's not falling. And so our derivative graph is going to be interesting, because it's going to be lying completely on the x-axis. It's not going to rise or fall, and we don't need any values that are positive or negative. However, because of these points of discontinuity here, there is no slope at those points. So at every integer, there's going to be an open circle. So our graph of f prime looks like this. So anytime the slope changes value or doesn't exist, the f prime graph is going to be undefined, non-existent there. So looking at number 9, we have this part that has a slope of 0, it's flat. Then this portion that has a slope of 1, and then this portion that has a bigger slope, could be 2, but it doesn't change gradually like a curve. It's an instant change. So let's see. 1, 2, 3. So at 0, right here, it still has a slope of 1. But if I back up to -1, here's where the change happens. Before -1, it had a slope of 0. But then it changed. At -1, it changed and became a slope of +1. And then after 1, then it grew to a slope of about 2, we'd say. And so here is what our f prime graph will look like. All right. So now, looking at number 10, here we have points on the graph that almost have a slope of 0. Right about here, but they're very slight, because this is a logistic function, and a logistic function has a horizontal asymptote up here and a horizontal asymptote down there, which means that as x approaches infinity, the slope is going to approach 0, as is when x approaches -infinity. It'll also have a slope that approaches 0. But in between that, we have a slope that is positive. And if we have to estimate, that's roughly a slope of about 3 at its highest. But then, as we move closer to positive infinity, the slope goes down and becomes closer to 0. And it'll go the same way in the opposite direction because the graph is symmetrical. So here we have f prime of x. So looking at number 11 now, here, this is a logarithmic function. The slope is never 0. Here it's very positive and it's going down. Now the difference between a logistic function up here and a logarithmic function is there is no horizontal asymptote. It's continuing to grow. However, it is growing at a slower and slower rate. And so since it's undefined over on the left side, we don't need to worry about defining that part of our derivative graph. And so our slope starts almost infinitely high. So it's going to start way up here. And then as it levels off, it's going to come down, come down, come down. Now it's going to stay positive, but it will approach 0. Because if you think about what is the derivative of ln, that's 1 over x. And all other logarithms follow the same pattern. It's 1 over something. So that means we're looking at part of the reciprocal function, like we saw earlier in number 4. And then finally, number 12. Now here we do have a point where the slope is 0, where the tangent line is horizontal. Before that, we have a positive slope, and after that, we have a negative slope. And we're only defined between -5 and 5. 1, 2, 3, 4, 5, x and y. And so at 0, we have a slope that is 0. But as we go forward from 0 to 5, the slope is negative, and then it becomes more and more negative until it's infinite. And so it's going to have a vertical asymptote at 5, and then also symmetrically at -5. We'll also have a horizontal asymptote. Okay. Hope this helped. If you liked the video, please give a thumbs up. For more videos like this, click the subscribe button. If you're a teacher and you like this, think about sharing this with your students. If you're a student and you like this, please share it with your classmates. If you have suggestions or problems you want to see worked out, type a comment below. To support the channel, click the Patreon link to help keep this going. Thanks so much for watching. And remember, the only way to understand something is to do it.